Hello students, welcome to Smart Structures and Application class. In this class, let us study something about the actuator materials. We have got different types of actuator materials. Let us study what are those types and what is the working principle and science behind that. The actuator materials are of basically six types. We are discussing only about the basic type. First one is the piezoelectric, second one is the electrorestrictive, and third one is the magnetostructure, and fourth one is the shape memory and the electro-rheological fluid, and sixth one is the electromagnetic actuation. The first one is the piezoelectric. On this presentation, you have got one crystal. When the crystal is pressed, you can find some changes in the voltage. So piezoelectric material produces some voltage when stress is applied. So this is the basic, concept of all digital electronics. A crystal when a load is applied or when it's stressed, it will produce voltage or it will produce pulses. So without piezoelectric application, we cannot go for modern science and technology. And every, even in your computer or in your cell phone, everything has got crystals, and based from the crystals only you are generating the pulses, electric voltages. So this is the one of the type. Piezoelectric is the when material is stressed, it will produce voltage. Here in this presentation, you can find the material sample is pressed, and you can change the changes in the voltage meter. It is connected next to that. And the second one is the electrostrictive material. Electrostrictive material. The electrostriction is a property of all electrical non-conductors or dielectrics that causes them to change their shape under the application of electric field. It is a material which will not conduct any electricity or the dielectric or non-conductor. When the material is not, when the electricity is applied to the material, it will change its shape. The material, so we are making use of this change in shape for the applications in the smart structure. All dielectrics exhibit some electrorestriction. Certain engineered ceramics known as relaxer ferroelectrics. Those materials have got extraordinarily high electrorestrictive content because we are using some material for our application smart structures. If anything changes its shape due to the application of electricity, without electricity and magnetism, smart structures devices cannot be made. So whenever when you are applying the electricity, the material shape changes, you will be in trouble. So we have to go for this property should be under control, or there must be some limitation for this property. And we have got three basic types of the material which is showing very high electrorestrictive content. The first one is the lead magnesium niobate. The second one is the lead magnesium niobate lead titanate. Third one is the lead lanthanum the zirconate titanate. So these are the basic materials which have got high electrorestrictive content. So these materials may be used for smart structure application. The third one is the magnetostructive. It is it is similar to electrical property. And here suppose if a material changes its shape due to the changes in magnetic field, it is called as magnetostructive material. So magnetostructive materials exhibit change in shape under the influence of magnetic field and also exhibit change in magnetization under the influence of mechanical strength. That is, it's controversial. So when you change the magnetic field, it will under it will change the shape. When you change the shape, the magnetic field will be very. This is another thing. The magnetorestrictive materials can convert magnetic energy into kinetic energy, or the reverse. It can convert kinetic energy into magnetic energy, or magnetic energy to kinetic energy. The property is quantified, it is mentioned by magnetostrictive coefficient, that is delta. The symbol shown here is capital delta. As in English letters, we have got our Greek letters of the capital and small letters, capital case of delta, which may be a positive or negative, and it is defined as a fractional change in the length of the magnetization of the material increases from 0 to saturation value. So this concept may be, it can be negative, positive, it can be positive or it can be negative. It will show changes in positive direction as well as negative direction. And this, suppose this effect is responsible for the familiar electric hum. So we can hold, I mean, in choke tube lights in choke, we can find some hum noise. In motor also some hum noise will come. So that the hum noise is due to this kind of property. And there must be some change in the shape and making some friction. And whenever the electric magnetic field is changed, shape is changed. So one material, it is it makes friction with the other material, so the hum noise comes out. Other interesting thing, the shape memory alloys. Shape memory alloys is nothing but the alloy that remembers its own shape. So whenever a load is applied, the material will be deformed and it will remember the own shape. Whenever it is being heated, it will come back to the original shape. Shape memory alloys is an alloy that remembers its original shape, and that when deformed returns to the pre-deformed shape when heated. So when you apply load, the material will change the shape. When it is preheated, then it will come back to the original shape. This is a shape memory alloy. It is also very useful in the application of smart structure. This material is lightweight and solid state alternative to the conventional actuators such as hydraulic, pneumatic and motor based system. This is widely used in hydraulic application, pneumatic application and motor based system, and it is of course a solid state alternate to the conventional actuators. And shape memory alloys have application majority, more applications in robotics, automotive, aerospace and biomedical industries. And then comes the electro-rheological fluids. Electro-rheological fluids are suspensions of extremely fine non-conducting but electrically active particles. This is of course is neither a pure liquid or it's a solid state. It is suspended in a colloidal form. It can conduct electricity, and so it is of course extremely fine and fine. It will have fine particles and which can non-conducting, which are fine and non-conducting, but it is electrically active particles. These particles may be very fine and non-conducting, but it is electrically active. It won't conduct, but it is electrically active, and its diameter will be 50 micrometers in diameter. That is 50 by 10 power 6 meter. The apparent viscosity of the fluids can changes reversibly in an order of up to 1 lakh in response to the electric field. So the viscosity of the fluid will vary when electric field is applied. So it is in reverse order. When electric field is very high, the liquid viscosity will be low. When it is reversible, it is changing. For example, electrorheological fluid can go from the consistency of a liquid to that of a gel and back with response times on the order of milliseconds. Within a millisecond, within a nanosecond, it is a very fraction of a second, it can change it from shape to shape. State to state. The liquid state to gel state and gel state to liquid state in a fraction of time. The effect is called as Winslow effect. You may get, this is to be remembered. That is, this kind of effect, we change in viscosity in nanotime, in fractional by milliseconds. It is called Winslow effect. The applications of electrorheological fluids, because this has got more application in the modern equipment. So let us study some of the applications of the electrorheological fluid. Fast-acting hydraulic valves and clutches with separation between plates being in the order of 1 mm and applied in potential being in the order of 1 kilovolt. So we are applying 1 kilovolt volt and we are changing the viscosity. So you know the mechanism, clutch mechanism and hydraulic valves in the automotive and other highly in high-end equipment like aircraft or high-speed trains. So clutch plates are nothing but it is engaging the gear wheel to the engine. It's a connecting plate that engages the gear wheel to the gearbox to the engine. Once the clutch plates are detached in sense, the engine will be rotating freely and it will not, the vehicle will not move. When it is clutch is engaged, then the energy from the engine will be transferred to the gear wheel, and from to the gear wheel to the wheel, then vehicle will be moving. So that there must be now the plates are being used when springs are used. So we have got two contact plates. The plates are pressed very tightly. So this plate will make the other plate to rotate, like that it's being now. Now we are using the fluid to make connectivity between these two plates instead of just contact, frictional contact. Now the clutch plates are run by frictional contact. And here we are using the fluid to make it to run. So it is very effective, very responsive, and we cannot find some play in the clutches, and it will be very useful and effective. Common applications are in brake. Brakes are to be very, responsive. It should act in a fraction of time. So we are using this electrological field to apply for the, because in all manual brakes, when you press the brake, some hydraulic energy will be supplied to the disc, and from there a grip will be holding the disc. So it will take some milliseconds. So these fluids are more fast than the manual brake. Potential uses in accurate abrasive polishing, because in polishing machine, one surface will rub the other surface. So it has to be manually controlled to go for the polishing. Go for continuation of the polishing. Here we will be using this fluid to make frictional contact more, so that the polishing is uniformly done, and there is no undulation in the surface. So it is more effectively done. So these are the basic applications of this fluid. This electrological fluid. Here, one more major application is there. That is, ER fluid has also been proposed to have potential application of flexible electronics, with the fluid incorporated elements such as rollable screens and roll schemes and keypads, in which viscosity changing qualities of fluid, allowing the rollable element to become rigid for use. So, for example, in the modern digital electronics, we have some rollable screen. It's a computer screen, or electronic keyboard, or a TV. We can roll it out. So this is here we are using this fluid. When some voltage is applied, the roll becomes stiff, and whatever is being rolled is becoming a straight film. So we can operate that is for the electronic media. So this is we need not manually roll. We may not manually stretch it out. Instead, we can apply the electric volt, so that the screen itself will become straight, and it can be electrically or electronically used. And advantages of ER fluids. ER fluids device can control more mechanical power, so it gives more mechanical power than the electrical power. So it acts as a power amplifier. The advantage is speed. The major advantage is speed of its response. Almost complete liquid to solid phase can be obtained when the electro-rheological fluid additionally experiences compressive stress. The effect has been used to provide the electro-rheological braille display and very effective clutches. So it is the major use of this electro-rheological fluid is braille. You know that braille in sense, letters for blind. Blind will touch the surface and they will recognize the letters. So those things can be created with the help of this electrological fluid. In sudden change, we can continuously, suppose with a single screen, suppose if a blind want to read a paper, it has to go for many number of pages to turn over the pages to study. With a single screen, they cannot read. So suppose if you make any screen like that, and so that in a fraction of a second the letters are appearing and disappearing, that may be helpful for the braille to read. So here it is more, got more applications. And it has got disadvantages also. Advanced ER fluids can only tackle the problem. Ordinary ER fluids cannot tackle the problem. Advanced, you need some advanced rheological fluid. So that should be incorporated with the magnetorestrictive rheological fluid also. So the electrorestrictive rheological fluid and magnetoreological fluid are to be in line. So it requires combination of these two properties, and it is an advanced system. Another problem is the breakdown voltage of 3 kilowatt per millimeter is required to operate this one. This is also one of the disadvantages. This is about the range. and electromagnetic actuation. So I have already told about the in actuator technologies, that is electrical energy and mechanical energy combined together, and once electrically controlled, it is to be magnetically operated, or it is magnetically induced, or it should be electrically operated. Just electrical application, just mechanical application cannot exist. So the electromagnetic actuation is electricity and magnetism are interlinked. Without magnetism, there will be no electricity, and with the electricity, we can generate magnetism. So a special type of actuator is electromagnetic actuator. So combining these two effects is a special type of actuator. The control variable for this actuator is electric current, and the acting variable is force interaction. Because the control unit is electric power, and the force exertion or the actuation will be somewhat mechanical. The principle of transformation in these actuators is based in force interaction in a magnetic field. Principal operation is force operation in magnetic field. Magnetic field is the thing which converts the magnetic energy into the mechanical energy, and that magnetic field is controlled by the electrical unit. Electromagnetic actuators are used in many applications, from small devices to robotics. So to the robotics and nuclear reactors. Nuclear reactors where where usually the people will not go nearer when it is being operated, and it is very dangerous. So in those things, fine control of nuclear energy and for nuclear reactors to operate, we need some fine control. These are all activated, and it has been done by electromagnetic actuation system. And an electromagnetic actuation system, basically it will be like this. Two basic parts. One is the electric circuit, other one is the magnetic circuit. Electric circuit is the outer one, the magnetic circuit is the inner one. The magnetic core will be freely moving, so that the magnetic core will be inserted in a non-magnetic material, so that it can freely move. It is shown in the figure. This is the basic structure of that electromagnetic actuator. Movable core is placed inside, and the outer thing will be the electrical circuit covering. So the current in the coil produces magnetic field that gives rise to the Maxwell force that gives rise to the Maxwell force, which acts on the ferromagnetic core. Electric circuit or electric winding is done. Power is given to the electric winding, so that it will also become electromagnet. That magnet makes the magnet to move. Real magnet to move, or mechanical actuation is happening here. This is what about that is actuator material, and with this we come to the end of the fourth unit. Thank you.